Hello everybody, this is Yunwoo Kang and welcome to this video cast. This time I'll be talking about the Pythagorean Theorem. The Pythagorean Theorem. I said that wrong. The Pythagorean Theorem. Like last time, I'll explain a short history of this word. So, there was this old man called Pythagoras. 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 And he was like, oh, triangles. He said, oh, triangles. Triangles are so cool. And he made the Pythagorean Theorem. So what this is about is when there is a right triangle, let me draw this here, change color, with sides A, B, and C, a squared plus b squared always equals c squared. And this is when c, whoa, there's lots of lag, is the hypotenuse. Hypotenuse. We learned what this is last time. It's the angle, it's the side on the opposite side of the 90 degrees angle. So let's put this into better context. When there is a triangle, draw this, with the sides of 3 and 4, what is h? Well, it's dandy good that we just learned this Pythagorean theorem. We can just plug this in. 3 squared plus, this is a right triangle. 3 squared plus 4 squared equals h squared. So 9 plus 16 equals h squared. Yeah? So 25 equals h squared, and we just square root both sides. And this means that 5 equals h. h equals 5. We learned that. So we can know that h equals 5. So at this point, you guys are probably asking, why does this work? Why is this even working? This is really insane. Well, it's good that some smart people all the way back in the BCs, like I said before, discovered a proof for this. This was called Euclid's proof. Euclid is another person. Euclid's proof of the Pythagorean theorem. Surprise, surprise. And this was quite the complicated proof. Euclid was a smart man, and he wanted to prove to everybody that the Pythagorean theorem worked. So he created this object here. This is a right triangle ABC with the sides of A, B, and C. Small a, small c. Here, he made a square for each side that resembled the lengths of this side of the triangle. So this would be C, C, and C, and so on. So I'll erase these. It'll just make it more complicated, so I'll erase those. And here, we can know that FBC, so triangle FBC, let's draw this here. Triangle FBC. My drawing has gotten better, hasn't it? It's this tablet. I'm used to it now. So triangle FBC equals the triangle of FAB. FAB. Why? Simply because it has the same base of FB and the same height of AB. Same height of AB. Both of these triangles have the base of FB and the height of AB, so they are the same. Simple enough, right? Well, there's another part of this. It also says that ABD, this triangle right here, so triangle ABD is equal to triangle BDK. Alright? At this point, these look pretty useless, but this is where it gets really interesting. Say that we both know that angle FBC right here, FBC, this angle right here is a 90 degrees angle, this one, plus the angle of ABC, right? Right? Funny enough, the angle of this angle right here, angle ABD, is also a 90 degrees angle plus the angle of ABC. And because of this, using the SAS congruency theorem, we can know that all of these angles, all of these triangles, are congruent. Okay? All of these triangles are congruent. This triangle here, this triangle here, this triangle here, and this triangle here are all congruent. And in a similar way, well, let's not get into that yet, and because of that, we can know that triangle BDK times 2 equals the rectangle BDLK, and triangle, what's this, FBA times 2 equals square FBAG. And because all these triangles are congruent, let me erase this here. Because all these triangles are congruent, so are these. Equal area. We know that. So at this point, we know that FBAG and BDLK are equal, these two here. And in a similar way, we can see that the square AHIC is equal to this rectangle KLEC. So these two are also equal because of a similar manner, but with triangles on this side. So just pause the screen and think about this for a moment, and we'll move on to the next part. There? Okay. Let's move this whole object over to this side of the paper where there's nothing else here. And at this point, we can see that length side BC squared. Oh, never mind. This was a bad idea. So we can see that BA squared, or this square here, and this area, since this area is equal to this area, equals BD times BK. Simple enough, right? And also here and here. So this angle right here, AC squared, this side right here, AC squared, is equal to this rectangle, so KL times KC, right? And when we add all of these together, we can know that all these together equal all four of these objects or shapes added together. And at the start, I explained that this square here plus this square here equals this square here, right? Or if I didn't explain that, I'll explain it now. It's like that. So because of this, we can know that BD times BK plus KL times KC equals, and since BD and KL are the same, it would be a BD BK times KC. If we use some distribution and stuff here, or what's the one that's opposite of this distribution? I don't remember, but that's what we use to put these all together. And since BK, right here, BK times KC, oh, plus KC, I'm sorry guys, it's just a problem I have. Plus KC, you guys are probably shouting at the screen, plus KC equals the angle on the side of BC, this equals BC. We can know that BA plus BA plus BA squared plus AC squared equals this whole square, which happens to be BD times BC, which is BC squared. And because of this, we can know all together that BA squared plus AC squared equals BC squared. And these just happen to be the sides of this right triangle, which are A, B, and C. So this would equal A squared plus B squared equals C squared, therefore proving the Pythagorean theorem. I'll see you guys all in the next video. Thank you for watching.